we've been doing some work in student persistence, and we'd like to present new packages for sharing with you the data. So there's new data available now, and also the methods and the metrics for studying student persistence in higher education. One of the common techniques for studying students in higher education is to use cross-sectional studies. They do have some advantages. One of their disadvantages, though, is that it's very difficult to study students who don't enter with the cohort or migrate between majors or drop out and come back. You need longitudinal data for that. With these disadvantages, longitudinal studies allow us to take a look at students across time, and we can look at the same groups over the whole period. So for example, every student who starts has a first year, and as they continue, students who stay in school, every student has a second year and a third year. And so we can aggregate the students in that way and look at them longitudinally, which allows us to examine the pathways that are not traditional. So students who change majors, students who migrate, students who transfer, all can be included when you're looking at them in a longitudinal way. So there are some advantages. The difficulty is finding longitudinal data. Well, that's what we have. So the Midfield project is the database. The acronym stands for multi-institution. So currently we have 21 institutions all in the US. Multi-institution database, there's the D, that's the important one. FIE is for investigating engineering. So it started out as a project for looking at engineering students, and then the L and the D are longitudinal development. But you don't have to study engineers to use the database because it's whole population data from the registrars at the 21 institutions. So we have data for all majors for the 20 plus years of data that we have. So it's 1.6 million students in the database total. And of course it then is suitable for longitudinal study. The Midfield data are curated. Please come in and have a seat. The Midfield data are curated in these 4 bins. Students, so that's individual student information like demographic data, the term data, course data, and of course graduation data. What we've done is we've extracted from the Midfield data set a stratified sample. And that's what's in the Midfield data package. I'm going to talk about 2 packages today. The Midfield data package has 98,000 students from 12 institutions. And again, we have those 4 same bins of data sets available. In the students category, we have demographic information. In the terms category, we have 1 term per student. So the number of observations goes up from 98,000 to 730,000. Then we have the course data set, which is the largest. That's 1 course per student per unique term. And so this is the big one, 350 megs of memory if you have it installed, which is why this one won't go to CRAN. Okay, this package that contains the 4 data sets is going to be it is hosted on GitHub, and it's in what's called a DRAT repository, which allows us to have Midfield R package access that, and Midfield R then can be accepted on CRAN. It's not yet, but it should be soon. And then we have degrees. This is the degree information for the same 98,000 students. These 4 data packages, it's 1 data package. These 4 data sets are all connected by the student ID, the institution, and the term, all of which have been anonymized. So the student ID is unique to the Midfield data set, but it's been anonymized. You can't track it back to an actual human being. And of course, the institutions have also been anonymized. Now, you can find out more about the Midfield project and what institutions are involved. There's a website devoted to that, which you can ask about later if we need to. So we have those data sets in the Midfield data package. The other package is Midfield R. Midfield R is where the functions live that will access the data and allow you to compute student persistence metrics. And I'll give an example in a little bit. So there's the data and there's the tools. Both packages are on GitHub, and you can see their status bars. I could have submitted to CRAN, but it's not quite stable. I want a little bit more time to make sure that I'm erased all the easy mistakes first before you all get a hold of it. But anyone that is interested, they're on GitHub. They've passed their R command check. At least that much we know works. And you're welcome to join us and find all the mistakes so that we can fix them. So there's the two packages. And of course, for this audience, we probably don't have to answer this question. It should be fairly obvious, but we would like, because data like these that are longitudinal for higher education are not generally available. Even folks doing research in their own institutions have difficulty getting hold of their own institutional data for doing research on data like these. And so, so the first thing we want to do is share the data, and that's why we have the stratified sample. And then what we also want to do is share the methods and the metrics, because over the years that we've been working with these data, we have developed some of our own persistence metrics. I'll show you one in a minute, that are not conventional necessarily, and we'd like to promote their use and comment and review folks that might be interested in this. So, and of course, R is the community in which to do that. So those are that's our sort of motivation behind providing those packages. So let me stop for a minute and talk about one of those methods and metrics that are unusual. You may be familiar with graduation rate as a metric, and the way it's defined. It actually has some limitations. And we have a substitute. Instead of graduation rate, we have a substitute metric that we call stickiness. How sticky is a program? And we define this as how many students did you have that graduated? And the stickiness is the ratio of that number to how many students ever enrolled in your program. Not just at the beginning, but ever. They transferred in, they came in, and they stayed for one term and left. Because these are the students that you actually had in your program. You had a chance to graduate them because they enrolled in your program. So stickiness, we think, is a nice metric because it accounts for all of the students, whether they transferred or changed majors, whatever they did. If they touched your program, you had a chance at holding on to them. And so we have this persistence metric that we call stickiness. And here it is, N graduates of a program divided by N ever enrolled, and we thought it might be fun to compare, because we're all engineers, the stickiness of engineering to stats and applied math. I lumped those two together. So I'm eliminating the pure mathematics students, just looking at stats and applied math. Different programs might call them different things. So I thought we might look at that and see that. So to start on that metric, the first thing we need to do is define what's called the classification of instructional programs code. This is a national level US encoding for programs. It has a 2-digit level and a 4-digit level and a 6-digit level to describe every program. And so we have the CIPs saved as a data set in Midfield R, which we can access using the CIP filter function. By the way, the tidyverse is all over the place in this functionality. And so because I'm using filter in the same way that the tidyverse uses filter, I simply added the CIP underscore. So we're filtering in the same way that you would expect it to be used in the tidyverse. So you can use, yes?
So I think before you were describing your data in terms of courses and terms, but not in terms of programs. Was programs in there?
Yes. It's in the term record in every one of the data sets. There's student ID, and there's a program code for what program they're in, what major they're in that term. And when they enter, and when they graduate, that data is in there. And so we go to CIP and we filter for finding the programs that we want. Here, I wanted to look at engineering and math and statistics. So here's the output of the CIP filter. And it turns out that applied math and statistics, and then the math and statistics other, there are 3 codes there that I used in this little demonstration. I simply ignored the first one, the 2701. You don't have to know these codes. You can use the function CIP filter to just search on strings. And so if you type in math, you'll get a whole bunch, and some of them are the ones you want, and some of the ones aren't. But that way you can explore the data without knowing ahead of time. Engineering was easy. The 2-digit code for engineering is 14. Anything that has 14 in front of it is an engineering program. So I use CIP filter to find those 2. And then what we do is we want to get 2 things. In order to compute stickiness, we need to know how many students ever enrolled in those programs, and how many students ever graduate, or how many students graduate. So we have a function, the ever filter. And it goes into the Midfield terms data set and finds every student that was ever enrolled, even for one term, in that program. And of course, many students will enroll in the same program for multiple terms. Okay, so the EverFilter will get rid of those because you want unique students when you're counting them. So EverFilter does that. This is the output of that. You can see you have a unique student ID that's been anonymized. And we have the program name, which is engineering. And later, if you go down to those 20,000 rows, you'd find math and statistics and applied that we talked about earlier. So we have about 20,000 students that are from the data set that were ever enrolled in either engineering or math and, applied math and statistics. That number, by the way, is a little bit higher. There's a thing I've got to fix because we're counting students that were ever in the program. But since you're talking about graduation, you should be talking about what we call the possible graduation in 6 years. So the end of the database here is 2016, this one? 17. So if the student was enrolled in engineering in 2017, but they'd only just started, the database ends in 17. So it was not possible for them to graduate. So I need to, what I haven't done yet is added the filter that removes those students that they couldn't possibly have graduated, so you can't use them when you're counting them, right? Haven't done that yet. That's one of the reasons I haven't put it on CRAN. I want to wait until I get that corrected. So this number of 20,000 is actually a little bit high, but for demonstration today, it's okay. So then we want to look at, we often do intersectional research where we're looking at the intersection between race, sex, and program. And so we have a function race-sex join, which goes to the student's data set and finds the student demographics and joins it in the tidyverse sense. Left joins it to the data that we're collecting. And then we group and summarize in the usual way. So we have, for example, we have 302 Asian females ever in engineering in this data set. We have 998 Asian males ever in engineering in this particular set, and it goes on. So I've already mentioned the possible grad 6. So there's the ever enrolls. You can see I've got program, race, sex, and ever. Ever is the N. So we do the same thing with the graduation filter, except it goes to the midfield degrees data set and looks for graduates that have the same programs. And so once we have those, we do the same thing. We join race and sex. We group by program, race, and sex, and count them up. And there we have the graduates, about 7,500 graduates out of that 20,000. But like I said, the 20,000 was sort of artificially high. And once we have those, well, now we just join them again in the usual way. We join the graduated to the ever enrolled. We compute stickiness, which is the ratio of how many graduates to how many were ever enrolled. And one little wrinkle, we remove any populations for whom the population is 5 or less. Part of that is to protect, for confidentiality, because if a program only had one Native American student, you might actually be able to identify what student or what institution it was when you're doing the analysis. So even though the students are anonymized and the institutions are anonymized, it's been a practice of ours to pick some number 5 to 10 and not show results that are less when there are fewer in the population than that. And then we plot the stickiness using the conventional ggplot functions. Here's the answer for this particular data set. And this would indicate that the median of engineering stickiness is a little bit higher than the median stickiness of the math and applied math and stats group. I thought the interesting thing here was the big disparity in the grouping. The statistics and applied math data are spread out over a much higher range of stickiness. Engineering is somewhere between 20% and 50% of the students that ever touch engineering stay there. And the applied math and stats goes between 10% to 70%. These are Asian males out here. So apparently, at least in these data, they're very sticky to statistics and applied math. And the interesting thing I thought, the one other interesting thing was that we have whites and Asians. Of course, these are US categories that are clumped. Whoops, let me back up here. Clumped up here at the top, and people of color clumped down at the bottom. And that disparity is much more obvious in the statistics and applied math group. Now, one of the disadvantages of the one I've shown you here is it's only 2 groups. I mean, if we looked at an entire institution and broke it down by, arts and humanities and so on, the ordering of these rows would be much different. Of course, the ordering is going to be based on what data you're using. But I thought it would be cute to look at that for this group. So, yes, please. The dots missing, thank you, there were fewer than 5 students ever enrolled in that program. So now you can have a 0 stickiness. It means you brought in 10 students and none of them graduated. That would be a 0. So 0 is possible. It's much different than an NA, or in this case, we have no Native American females or males, and oddly enough, no Latinas in that group, which I found surprising. But what that means is, according to the algorithm I was using, there must have been 5 or fewer Hispanic Latinas that were enrolled in a math or stats program, which there's 98,000, no, there was 20,000 students total we were looking at here. And it was surprising to me to find no Latinas in math or statistics. So what that does, of course, it raises the question is, well, you have this sample of 98,000 students. Is it really representative? Well, we think it is. And so when we have findings like this, that might lead us to that next question. And of course, you all can help if you're playing with these packages and you find things that strike you as being odd. Those are things that might help us revisit how the sample was originally obtained. Because remember, we have 1.6 million students and we've sampled 98,000 of them. Okay, so if you're interested in more, there's a GitHub website built with PackageDown, so it's got all the usual things. There's several vignettes there. I've only sort of scratched the surface, but there's a lot more there that's available for you. If you're interested in the project, we have links to the Midfield project and an email for that project. And I think I'll stop there, and I'm happy to answer questions. And anything I don't know, I will turn over to my colleagues, because they are the experts. Yes. Oh, thank you. Thank you.
You were explaining your sampling, so I wonder why couldn't you use a whole data set, which is only 1.6 million, which is not big?
It's 1.6 million students, but the courses is 1 course per student. That gets huge.
No, it's every course. It's 1 record per every course the student took.
Yes.
So,
Right, so if you back up to the little picture here, right here. So 98,000 students, 3.5 million course observations. That's my 2-minute warning to myself. So that does get very large, right? And even this one with just 3.5 million observations, when you install this package, you sit there and wait for just a moment for R to sort of catch up, right?
I'll also add, if we were to give you the whole data set, it would violate our agreement with our institutions who don't want to be identified. So if you had the full set of demographics and the enrollment, you could essentially figure out which institution is which through the data set, and that would be a problem for them. Yeah. So that's the other reason to use a proportionally sampled data set.
I probably have time for one more question.
Have this data set get used within institutions?
Matt?
How does it get used within institutions? Well, so one way is some institutions, people at those institutions have less data access than we do, and so they actually reach out to us to ask questions of their own institution. But other institutions are actually getting into the process of comparative analysis. And they're quick to do that as long as they don't publish it in an identifiable form, so they can use it internally for policy decisions. So we have an institution where their policy for allowing students to maintain enrollment subject to a very low GPA, very low level of performance. It was allowing students to dig a hole so deep that there was no way they could take enough courses to get themselves out of it and be successful. And so that actually resulted in a policy change where they made a stricter requirement for continuing enrollment. So there have been a number of schools who use it in various ways like that. And we're encouraging more and more of that. I don't know if we have any more.
We don't really have any more time, but we will be around after the session. If anyone would like to talk to us, we'll be here, all 4 of us. Stand up quick, let them see who you are. There you go. Thanks.